All right, any questions? All right, today's topic is a fun one because it's a graph problem. Everyone likes graph problems. It's called Sparsest cut. Uh, I'm slightly concerned about whether we'll be able to cover it in time. So let me not remind us all the things we've been doing recently. Well, I should mention, last week when we did dimensionality reduction with the Gaussian random variables and going from high dimensions to log n dimensions, this question came up of what about metrics besides L2? What about L1, L infinity? And so that's why I decided to do this lecture, because this lecture is actually really about doing embeddings into L1 metrics, and we're going to use that to solve the sparsest cut problem. In fact, I taught this topic last year in an advanced graph algorithms class. I was thinking of skipping it this year, but since that question came up, I thought we'd do it again. Besides, it's a fun one anyway, and I think we only have like one overlapping student who likely was asleep that time. Okay, all right. So anyway, today's about sparsest cut. Two things we'll need. So it's going to be an approximation algorithm kind of thing. So we'll do some stuff with LPs. Uh, and I think we'll need to talk a little bit about LP duality, which is this very basic thing. I won't prove it, but it's good to know. But the randomized part is really going to come from these L1 metric embeddings. I'll explain that when we get there. Okay. So let me first, as a warm up, so sparsest cut is going to be kind of a flow and cut type of problem, but let me warm up with just max flow. I know we probably have hopefully seen it before because I'm not going to give too detailed of a description here. But at a high level, you have some graph. You want to know how connected S and T are. There's different ways to do this. But a popular one, for example, that we do in max flow is, how many disjoint paths are there from S to T, right? So, yeah, actually, maybe I can ask you now. In this graph, how many edge disjoint paths are there from S to T? Maximum number. Yeah, can anyone find two? One? Okay. How about this? We'll just start here, and you tell me whether to go up or down and whatever, and we'll try to see if we can find our way to T. Okay. Oh, okay. The undirected edge you can do whatever you want with. You can go both directions. Um, good. Attention to detail. Okay, I'm here. Should I go up or down? All right, let's go up. Should I go up or down? Up again? Okay. There's a couple. Oh, there's the famous undirected edge. Should this one going to the right? Okay. To the right again, like this, I guess. Okay, there's one path. Good. Let's try to see if we can find a second one. So here we're going like this. Any favorites? Up or down? All right, let's go down. So we only have one choice. Yeah. Now it up, up the left dish. Okay. Right, down. Oh, another famous undirected edge. Okay, good. We found two. Fine. All right. Uh, is that the optimum answer? But how do you know it's the optimum answer? Oh, okay. So there's an ST cut, right? If I remove those two edges, there's no way to go from S to T. So the number of paths I can pack is always at most the size of any ST cut. Here we have pack 2 paths, and then there's a cut of size 2 that certifies each other to be optimal. Okay, I know you guys have likely done this before. I have some pictures about why people study this, but it doesn't matter. Okay, so that's one problem, maximum number of edge disjoint paths, minimum number of edge deletions to disconnect S from T, the minimum ST cut problem, right? Okay, all right, so this edge disjoint path problem, we can think of as, sometimes in undergrad we do like the flow where you have like fractional values or whatever, and some inequalities. I'm not thinking of it that way. I'm thinking of it as a path packing problem where I'm packing paths into the edges, right? I'm trying to fit a bunch of ST paths, but each edge is only allowed to be used by one path. So it's a packing problem. I'm pushing things in, okay? And on the flip side, for this ST cut problem, where I'm trying to delete edges, so I can't go from S to T, I want to think of that as a covering problem, okay? So there's exponentially many paths from S to T, paths from left to right, but I want to take a set of edges, so I'm taking at least one edge from every path from S to T, right? That's the same as saying, if I remove these edges, there's no path left, okay? So it's just a change in wording, but then you start to see a little bit more of the duality, right? Because in one problem, I'm kind of packing paths into edges, and the other, I'm covering paths with edges. Okay, there's some nice symmetry there. All right. Okay, so, the question is, what are these quantities and how do they relate to each other? And we already kind of went over this, which is that the maximum number of paths you can pack in is at most the minimum number of edges in the ST cut. What's wrong? Nothing wrong? Okay. You're laughing at me and I feel insecure. All right. I guess we don't necessarily need to do the proof. It is an undergrad class. I guess I would have. But it's not really such a big deal. If you have any path packing, which I'm calling capital P, okay, and I sum over the paths, and I look at the intersection of the path and my cut, so C is a set of edges forming a cut, since the paths are disjoint, those intersections, P and C, don't overlap. Okay, so actually you would get less than equal to. Oh no, you would get equal to, sorry. Okay, so then you get the union of the intersection, and that's at most the size of the cut. Okay, no big deal. Should be intuitive. Fine. Okay, so that's one side of the maximum min cut theorem, and the question is, are they equal? You guys probably know that they're equal from your undergraduate class. Fine. But I want to give you a different proof than we typically do in the undergraduate class, a proof that's not combinatorial, but rather based on LP duality and randomized algorithms. It'll be quick. All right, so we've used this notation before, so I think we know dot products, transpose, stuff like that. All right, so what's the duality theorem? All right, so on one hand, we have a packing LP that's trying to maximize some sum of x's. Okay, on this side, I'm trying to maximize some sum of x's subject to some capacity constraints. Ax less than equals c is trying to say, oh, I can only take so much of each x. Right, so A will break out into a bunch of rows, each expressing a packing constraint. A covering problem is sort of the opposite. Rather than maximizing, I'm minimizing some cost vector over y. Okay, and now it's saying that, oh, y needs to have at least enough to meet each of these covering constraints. A transpose y is greater than or equal to b. Okay, so packing, I'm trying to take a lot of stuff, but it's fitting into something. Covering, I want to take as little as possible, but cover up whatever requirements. Now, I was careful about the notation. So here we see B in the objective on the packing side, and B is on the constraint side over here. Here we see kind of C, like capacities on the packing side. and they're now in the objective over there. They're like costs. Okay, we have A here and A transpose here, which means you're kind of swapping the incidences, so to speak. Okay, so in that particular arrangement, in other words, for any packing LP, there's this dual covering LP where I swap the B into C and I transpose A. Okay, and likewise for any covering LP, there's a corresponding dual packing LP where I just make that exchange. In that case, the values of the LP are always equal. Okay, so this is actually very valuable. So why it's kind of invaluable is let's say that we're interested in some problem that's naturally a packing problem, okay, and we're stumped. We can't think of ideas, right? This is sort of saying there's some equivalent problem that maybe has a different perspective on it, right? But the values are the same. And as we'll see, there's also some stronger connections too, usually when you open up the problem. And the dual problem is sort of the opposite side of the same coin. And it can give you some perspectives to develop some algorithms. Okay? And you get this equality for free. It's a very powerful tool. Okay? I won't prove it. It'll take a while. But it's true. Believe me. So let's apply this to max flow min cut. Okay? And this is why I wanted to think of max flow as a packing problem. Okay? So if I'm packing paths from S to T and I want to write now the linear relaxation, so I'm not worried about a discrete path packing. It can be a fractional path packing. Okay? Now I'm sort of trying to take as many paths as possible. Okay, so I'm letting kind of capital P ST denote like the collection of all S to T paths. There could be exponentially many. So this is not a small LP. This could be, if you wanted to write down all the variables, it might be exponentially large. I'm okay with that. Okay. So to every ST path, I assign some fractional value. Maybe it's 0 for most of them, right? A non-zero value means I'm taking some of this path. And I want to make sure that for every edge, if I sum over all the paths that contain the edge, it's at most the capacity of the edge, right? Like you expect in flow. In disjoint paths, I can only use each edge once or something. So the sum of paths using that edge would be at most 1. Okay. So this is a linear relaxation for max flow. Now the dual, so what the A transpose is kind of doing is if X packs into Y, then you're going to get Y covering X. Okay, because you're just kind of rotating things. So if we're packing paths into edges, we're now going to be using edges to cover paths, which we kind of already know. Okay, so the capacity here now looks like costs up here. Okay, and before the variables were paths, now the constraints correspond to paths. Before the constraints corresponded to edges, now the variables correspond to edges. Okay, so this is just doing the exact duality as before. Now our constraint is saying for every path from S to T, you have to take at least one total edge fractionally, right? Just like you have to take at least like an ST cut should. Okay, so this is sort of the ST cut LP. This is the max flow LP, but maybe in a different formulation than you guys have seen before. Okay. All right. Okay, so I want to show that max flow is equal to min cut, but when I say min cut, I mean minimum discrete cut, like set of edges. Okay. LP duality tells us for free that max flow, which is naturally like the fractional version of the problem, max flow is equal to the minimum fractional cut, so to speak, if I'm allowed to take fractional edges. Okay. And I know that since the LP is a relaxation of the discrete problem, the minimum fractional cut is at most the minimum discrete cut. Okay. So in other words, we're getting a lot of information for free. And if we could only show that this is at most the min fractional cut, then we would be done. We get max flow min cut. Right? Does that make sense? All right, so what we're going to do then is we're going to do some LP rounding arguments. Okay, So let's first imagine that we solve the LP, which gives us some fractional cut from S to T. This is not necessarily an optimum solution. I don't know what would be, but you get the sense that hopefully the length of every path from S to T is at least 1 with respect to these fractional edge weights. Okay. All right, so we'll compute the LP and we get a minimum fractional cut, whatever it is. All right. So what are we going to do? We are going to embed the vertices on the real line by distance from S. Okay. So here's S at distance 0, and then I'm just computing shortest path with respect to these edge weights that the LP gave me. Okay. So now, okay, so because the LP says that everyone has to have distance at least 1, T will be at least 1.0. Okay, it'll probably be exactly 1 because there's no point in going further. The LP otherwise wants to make the cost as small as possible. All right. Okay. So here I can actually ask you guys a question. Okay, so whatever. Right now we've solved the LP and we sort of interpreted or drew a picture and put it on the line. But really our goal is to find an ST cut that has value equal to the minimum fractional cut. That's our real goal. Okay, so if I can take my fractional solution and output a discrete cut of the same value, then great, then it's equal, right? So, all right, so I don't know if this is guessable. Any ideas? Uh, you could imagine so. The LP will take into account when it assigns the distances, and yeah, you can for the sake of exercise, but not necessarily. Okay, so maybe this is hard to guess. So what we're going to do is we're going to study a random cut. Okay, so imagine I have some value theta, and I choose some value between 0 and 1 uniformly at random. Okay, that splits the set of vertices into two halves, right? One's on the left, one's on the right. Since T is at 1 and S is at 0, any value in between will be an ST cut. There will be at least one vertex on each side. Okay, and what we're going to do is we're going to analyze the expected value of this cut. Okay. All right, so okay, yeah. So we pick a random cut. We output the set of edges that go across the line, which is dividing the left from the right. Okay, so I should have erased that, but that's okay. We'll go faster this way. All right. So what I'm interested in is what is the expected capacity of this cut. Okay. So by linearity of expectation, of course, we just need to figure out what's the probability of each edge being cut. Okay. Now, if we look at an edge like this down here, an edge E between A and B, okay, that edge was given some length YE from the LP, right? And, okay, so it's going from A to B, okay? And I know this is embedding the shortest path metric from S, right? So there's some shortest path to A and some shortest path to B that puts them on the line, okay? But of course, I can take the shortest path to A and then take edge E to B, right? And it would be A plus YE to get there. So whatever is the actual shortest path from B is at most A plus YE, okay? What that means is that this width right here is at most YE, okay? So the odds of this random theta falling between A and B then is at most YE, the value assigned by the LP, okay? So that's why we get that the probability that E is cut is ye, or at most ye for every edge. And then here we get the objective value from the LP. Okay. So we've shown that actually a random cut, an expectation, achieves the value of the LP. Okay. All right. Well, that's pretty cool. All right. Now, what's the final step? So we need to actually show that there exists a cut for sure that achieves the value of the LP. Then we'll get maximum in cut. Given this, how do I get there? I know a random cut and expectation is great. How do I know there exists a great cut? Yeah. Yes. Yeah, I think that's exactly right. I think you said at least, and maybe I would have said at most, or whatever. I think it's the same idea. So, you're basically trying a bunch of random cuts. In fact, you're only kind of trying up to n different cuts that could be separating vertices along the line. If all n of those possible random cuts, if they were all bad, then the average would have had to be bad. Okay. So in fact, at least one of them must be good. All right. So that's a probabilistic method. In general, if you have a random experiment and the average is very good, there must be some outcome possible of the experiment that's good. Okay. Right. So that's sometimes called the probabilistic method. Okay, but it's anyway. So that's our proof. Okay. If you wanted to turn this into a deterministic algorithm, how would you do it? Right now we can have a randomized proof, and I guess a randomized algorithm for outputting a good cut. Yeah. Yeah, try all cuts. It's not so hard. Okay. So we'll take this and we'll just scan it from left to right. Okay. Good. So now we prove maximum min cut. Right? It's much easier than Ford-Fulkerson if you're okay with LP duality as a given fact. If you wanted to prove LP duality along the way, it would have taken longer than Ford-Fulkerson probably, and less pictures. Okay. Fun stuff. Okay. Any questions about that? Okay, we're going to use these ideas in a more sophisticated way. All right. Let's go to our sparsest cut problem, the famous sparsest cut problem. All right, so let me just first give all the info. So we're going to be working on an undirected graph. There's positive edge capacities and like demands between pairs of vertices. Okay, so between every pair of vertices, there's some BUV, which I guess it could be 0 too. So I should have wrote greater than or equal to 0. Okay, and my goal is to compute. I have a picture coming up. Is to compute a set of vertices S that minimizes this ratio, which we'll call the sparsity. Okay, so in the numerator, I have the capacity of all the edges that are cut. So delta S denotes the set of edges that are being cut by S. Okay, so in the numerator, I want to minimize this. So I want the numerator to be small. So I don't want to remove too many edges or too much capacity of edges. Okay, in the denominator is sort of like how many pairs are being split up, weighted by this B. Okay, so I have these demands in the denominator, and I have edges being cut in the numerator. Okay, and my goal is to minimize this ratio. Okay, that's the general version. An important special case is when I take the demands to be 1 for all pairs. Okay, so between every pair of vertices, that the BUV is equal to 1. Okay, in that case, the denominator becomes simpler. It's just the number of vertices on one side of your set times the number of vertices on the other side. Okay. I think for everything we do today, you can just imagine we do this, although I think I've written it out in the more generic form. Okay. All right. So this turns out to be an incredibly useful uh, problem and an incredibly useful algorithm. We went through a lot of applications last year in the graph algorithms class, but a basic one is just for kind of graph partitioning and divide and conquer type of things with graphs. So let me explain. Let's look at this graph here. Right? Say you want to do divide and conquer. So you want to remove a small set of edges and roughly split the graph into like roughly equal parts. And then you can do something on each side, right? Okay. Now, before this lecture, the natural thing might have been like, oh, let's just get the minimum cut, right? That's the minimum set of edges to break the graph into two pieces. Okay. So what's the minimum cut of this graph? 1, right? All these leaves on the outside represent a cut of 1, right? Okay, so I could trim off one vertex and delete one edge, and it's really not making much progress in a meaningful way, right? Like it's basically the same graph left, and probably most real graphs have lots of leaves hanging off. Okay, so a minimum cut is not very useful. That's the dark secret. But um, now, what would the sparsest cut of this graph be? Or might it be? Yeah, yeah, the middle. So if I delete these edges in the middle, then I'm really, I'm only deleting 3 edges, and that's relatively small, and I break it up into 2 pieces. I keep most of the information insofar as edges represent information. Okay, so that's sort of what's going on. You know, if you look at the denominator of the sparsity, s times bar s, that's always maximized when s and bar s have roughly the same size, right? By MGM kind of type of stuff. So we are trying to split the graph and delete few edges, but try to keep it balanced at the same time per this ratio. Okay, and that's the idea of this problem. And yeah, besides kind of being useful for its own sake, uh, like for example, uh, mm, a very one problem is called balanced graph partitioning. So this one you're allowed to output graphs roughly of any size, and so as long as you have a good ratio. But in the graph partitioning problem, I'll say each side has to have at least n over 10 vertices or something, right? Like at least a constant fraction of the graph. So that's of course a very natural thing that you might want to do. You have a big data set, you want to split it up, you don't want to delete too many edges. So one algorithm is kind of just keep doing sparsest cut. So you get a sparse cut, and if they're balanced, everything turns out to have at least n over 10, then you're done. But in the bad case, you have one relatively small one and then a big one. So then you recurse on a big one, you get another sparsest cut, another sparsest cut, another sparsest cut, until you get like one big piece, and the small pieces can be thrown together to get another big piece. Okay, and that'll give you, I think, the best known approximation for this balanced cut problem. Okay, so sparsest cut is just a very useful primitive, and it solves a lot of problems in network design and stuff like that. Okay, it also has some connection to random walks that'll come up later. At some level, if you're doing a random walk on the graph, these sparse cuts represent bottlenecks. Like if you're walking over here, you're going to be stuck in this dense part, and it's going to be hard to get across a very sparse cut. Okay, so I screwed that up. A sec. All right. All right, so let's look at the sparsest cut problem. Hopefully that's not too small in the top right. Maybe it is. And we're going to try to take an LP-based approach. Okay. And so, okay, how do we write an LP for a sparsest cut problem? This is not as straightforward, at least in my opinion, as SAT and SAT cover and other stuff we've done. Okay. For example, one question that comes up is, how can I sort of, so I'm supposed to output a set of vertices. How can I sort of express a cut in a linear way, continuous way? Yeah, some kind of values between 0 and 1. So what gets what values? Uh, okay. So yes, this is the most natural thing. Okay, so uh, you can you can be and we're saying that kind of x0 means say not in cut, or maybe it's in S, and x1 means not in S or something like that. Mm, okay. Is this a good rhetorical question? Maybe not. Um, well, okay, here, let me give a different direction than I think is maybe surprising, but similar or inspired a little bit by what we did with Maxwell min cut. Okay. So what we did with the Maxwell min cut theorem was, if you remember the LP for the ST cut, it was really about making a metric from S to T was distance at least 1. Like all the paths from S to T should be at least 1. So there's some sort of kind of natural connection between metrics uh, and cuts. Okay. So, okay, so actually, I'll tie it to your idea in a moment. So, for any cuts, so okay, here's one way to think about it. So let's say if I fix a set of vertices S, okay, I could define a metric duv by saying that if u and v are both in S, I'll say if they have distance 0. If u and v are both not in S, then they also have distance 0. And if u is in S and v is not in S, or u is not in S and v is in S, I'll give it distance 1. Okay? So what we're doing is we're just kind of splitting the set of vertices into two parts, and if you have to go across the line to go from S to out of S, that adds a distance of 1. So that'll give you a metric. Okay? So there's this connection, or one way to one creative way to try to come up with a linear relaxation of cuts is via metrics. Okay? So Tower's trying to write an LP, then what we've done in the numerator is say, okay, now I'm asking you to choose a metric. Okay, so assigning distances between all pairs. One really nice thing about metrics is that their definition itself is a bunch of linear inequalities, right? The distance between any 2 points has to be at least 0. The distance from A to B has to be equal to the distance from B to A. And you also have the triangle inequality, right? Like the distance from A to B is at most A to C, C to D. Okay? So the fact that we can express metrics with linear inequalities is what kind of makes this feasible. So in the numerator then, give me a metric that's sort of like summing over the edges, and you can think of CE duv as like a cost of stretching edge E to distance uv. Okay, so you're kind of assigning distances to the edges, and you're paying some cost for it. And likewise in the denominator, we have those pairs that we're trying to split up. Now, as they get spread out, that makes the denominator smaller. Okay, so you kind of want to choose big edges to split up the UV pairs, but then you want to use small distances to decrease the cost in the numerator. Okay. All right, so that's pretty close. That's not exactly a linear program, though. Why isn't it a linear program? Yeah. Oh yeah, we have this fraction, right? So that doesn't, that's not a legal input. So how can I try to address the fractional part of it? The what? So if you do take the log, then you'll get log of something minus something, but that won't be a linear program because of the logs. Okay. So the things you have to work with is you can introduce as many inequalities and equalities as you want as long as it's linear. Yeah. A minus B plus some big constant. I'm just going to say no. Uh, yeah. Sorry? Too complicated. Yeah, too complicated. But okay, so at a high level, yeah, at a high level, we have A divided by B. And I can't deal with that. Yeah. Or you just tell me if this is what you're thinking. All right. So I have this issue of A divided by B, and I'm just going to say, oh, B has to be at least 1, and then otherwise minimize A. So I'm going to normalize it because everything is scale invariant. If I had multiplied all distances by 10, nothing changes because it's a fraction. Okay. So we're just going to normalize and say, oh, B has to be at least 1. The LP will always make it equal to 1. There's no reason to go above it. Otherwise, minimize A subject to B being greater than or equal to 1. Okay. All right. So the last one now is actually a linear program. Okay. We're sort of hidden in this metrics is a few more inequalities to force it to actually be a metric. All right. Um, so here, I spent like hours making slides about taking a dual, and I realized we don't have time to talk about it. So we'll skip it. Maybe the only thing to point out is that the dual of this problem, so for maximum min cut, the dual of ST cut is packing paths from S to T. And the dual of this problem is sort of trying to route a bunch of all those pairs simultaneously up to the demand BUV. So it's kind of like doing a max flow as many STs at the same time, and how much flow you have to send between each pair is based on the Bs. Okay, then we would have spent 20 minutes realizing that. Okay, all right, fine, but it's in the notes. It's good, but that problem is also very relevant, right? If you're actually running a network with many things talking to each other, you do need to actually route them over the same network with small congestion and stuff like that. So it is important. We just don't have time. Okay, so the randomized really part is really coming here. All right, so so we have an LP, this sort of metric LP, spreading metric LP sometimes it's called. I want to find a metric with minimum cost, so that's sort of like the spread, so to speak. This B times D is at least 1. Okay, and now we have to figure out how to turn a metric into a cut. Okay? Any crazy ideas? Has to be crazy. So you don't know anything about the D's. So the D's aren't they're not like sitting in some Euclidean space or something, right? It's only giving you distances. You don't even know like kind of what's underneath them. So it's not an explicitly embedded geometry. You just have a metric satisfying some inequalities. Like that's sort of the crux of the problem, I think, is that it's very abstract. Yeah, so LP will give you the D's. LP is choosing D's for you. So you have these D's. Okay. 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 So let's see. What are some things going on? So first of all, okay. So the idea was let's take the D's and randomly round to 0 and 1 or something like that, right? Okay. A couple things. One, it's not clear that the values of D are either very big or very small. So if all the B's were really, really small, then maybe all the D's are bigger than 1. But surely the answer is not to take all edges. If the values of B were really big, maybe all the D's are very close to 0, so much so that you almost output no edges. Surely that can't be right either. So there's some weird scale invariance issues going on, which I think was implicit in the ratio from before. It's sort of been flattened out now. So it's not clear that we can randomize round like we did before. It's not clear that D equal to 1 or D equals 0 indicates taking an edge or not. That's not really the interpretation. Yeah, I mean, we can try rescaling and then maybe try different scales and hope one of them works. Okay. Well, one issue that's going to be tough, right, is that what we really want to do is we want to sort of, for a set S, output all of the edges crossing that set. Okay. But if you're sampling edges, say, in proportion to these or something, you may be, and who knows, maybe you find a reasonably appropriate scaling first. But yeah, let's say you roughly round and sample edges where larger D's, you're taking the edge or deleting the edge, and smaller D's, you're hopefully not or something. But the edges you take are going to be kind of all over the place, right? They're not necessarily going to be concentrated around the neighborhood of a set of vertices. It's not clear that you even output a cut. You just output a bunch of edges. But it's not clear. There's no, compared to ST flow and cut, there's no sides here. Okay. So then as a warm-up then, let's suppose it did have a simple, uh, uh, some simple explicit reason underneath it, right? So as a warm-up, let's pretend it kind of like the ST cut stuff from before. Suppose that our metric was of the form, the distance between two of them is a distance between some two values, f of u and f of v, where again, f is embedding the vertices on the line. And since everything is scale invariant, we can just assume the minimum distance is 1, or no, the minimum distance should be 0 and the maximum distance is 1 or something, just to keep it simple. All right? Okay. So, as a warm-up, let's consider this special case. All right, now what might be a reasonable cut? Yeah, we can try the same idea from the Maxwell min cut. We pick some random theta and output it. um, and see what that gives us. Okay. All right. So, like before, then we need to calculate the expected capacity of one of these cuts. So S sub theta would be, say, the set of vertices to the left of theta, and then the expectation of the denominator. Okay. So you guys maybe remember how to do this. Okay. So how should I do the first one? The expected capacity of the cut. Yeah. So what do I need to do to get there? Or what do I invoke? So implicitly, we would be using linear of expectation where we break it up into the edges. The cost of E, the probability that E is cut. Right? And just like before, that should be at most the distance between the 2 points. So if the edge was UV, okay, which is exactly our objective from our LP, which is great. Right? And the denominator would be essentially the same thing. You can think of BST as being like edge weights of the complete graph. Okay. So the same argument goes through, and this time you get the sum over all E equals UV, the demand BUV times the distance UV. Okay. All right. So what's great then is that we have the numerator, right, divided by the denominator. All right. So what we've shown then is that this is equal to opt from the LP. Okay. This is good, but unfortunately, we're interested in the sparsity. An expectation of the sparsity of this cut is not equal to the ratio of expectations, right? So the expectation of sparsity is an expectation of the ratio, but what we've shown is that the ratio of the expectations is what's nice. Okay, so we haven't actually quite finished yet, although those calculations are useful. All right, how now? What I really want to show is that there exists, there exists a cut with very good sparsity. We haven't quite got there yet. There's some technical issues. Any ideas of how to address it? Good. All right, so I'm going to let lambda denote the optimal sparsity. Okay, and what we showed, right? So this thing is lambda. We showed that this is at most this, right? I'm just flattening out the ratio. Okay. All right. So what does that tell us? That means there exists, which you can also write as this minus this is less than equal to 0. But now that means there exists some theta where the value minus the value is less than or equal to 0. If it was always bigger than 0, then the average would have to be bigger than 0. Okay, so we just had to flatten it out first before otherwise doing the same argument. Right, so that kind of thing, and we're okay. All right. Okay. All right. So that's that does that special case where the distances was given just on one line. It turns out the same thing from Maxwell min cut works, and in fact, we lost nothing in the rounding. We got the exact same value. Yeah. Is also backwards. Yeah, yeah, you can take it back. Yeah, so we can do that. We can do this. Yeah, yeah. I guess we've never done that before, huh? That's pretty exciting. Okay. Hope we didn't break the law. All right. Okay. All right. Let's go one level up. Suppose you had a metric that was not one line, but it was a combination of a bunch of line embeddings. Okay, so let's say there's k of them. So the distance between 2 points is like the sum over k different coordinates of the line embeddings. Okay, so you have a bunch, and you're just adding them up. Okay, so let's say that that was the case, and you had access to the f's. Okay. What might we do here? Okay, same thing. Just expand a little more. Okay, we could randomly pick a theta. Okay, so if I randomly pick a theta, this isn't a great example because I drew the same graph, but you should imagine them actually being different embeddings with different vertices. But if I randomly pick a theta, and then I don't know, I could take maybe like the union of the left-hand side of each one, which would normally be different. I just copied and pasted the same picture, but or I could take or something like that. It's not even clear actually that you would get a cut because maybe the union of left-hand sides would actually be the whole set of vertices. Sure. Yeah, who knows how the analysis goes through, but I think the idea is we can try one of the FIs and do the same strategy we just did. Maybe we could do it to each of the FIs separately. Okay, so that means we just have to argue that at least one of the FIs are good. And one of the FIs also achieved the same kind of LP stuff, then we could have just done exactly what we just did to that one FI. All right, how can I argue that one FI is good? What's the chance that they're all bad? No. I don't think so. No, it's not going to be a probabilistic argument, actually. It's going to be even simpler. Not a bad idea, though. I mean, we're going to try to argue that they can't all be bad, which is probably similar to what you had in mind. How can I try to argue they can't all be bad? All right, so here's what we know. We know that if we sum over, okay, let's copy this. Oops. Okay. Okay, so we know the LP solution is good, right? So we know that this is less than equal to lambda times this thing, right? Where these distances are now given by this. Okay, so this is what we know. Okay. If I rearrange these sums like that, this is great. I don't have to write anything. Okay. So all I've done is rearrange sums, right? And I see sort of like what looks sort of like a sum of individual LP thingies. Okay. So one of these i's must be winning in this lambda contest, or else you wouldn't in the aggregate. So if every one of these inner sums was bigger than lambda times the corresponding inner sum, then the total would have to be bigger. Essentially the same kind of probabilistic argument, but not really so probabilistic this time, just adding things up. So at least one of the i's have to be good. As soon as one of the i's are good, we can do what we did last time. All right, so, all right. Okay. So what's the takeaway? If our metric was given as a sum of line embeddings, which is called an L1 metric. Okay? If it was an L1 metric, it can be rounded without loss. So L1 metrics can be converted to cuts without loss. Okay? Essentially from a probabilistic argument. All right, fine. Not done yet. Okay, so we come back to this question. How can I take a generic LP or a generic metric and round it to a cut? Okay. We now at least have one sort of weird approach, is somehow try to convert the metric to an L1 metric. Okay. So you're given a completely abstract generic metric only satisfying the triangle inequality and other basic properties. And we're going to try to find an L1 metric, and it won't be the exact same, that maybe approximates in a meaningful way the original metric. Okay. So if I can take a generic metric and find a close enough L1 metric, which will give me an approximate solution to the LP, from there I get a cut with the same value. So the only loss in approximation is going from a generic metric to an L1 metric. That make sense? Okay, so that finally brings us to really the heart of the randomized stuff. So I guess here's the theorems I copied and pasted so I don't screw it up. All right, so what does the first theorem say? If you give me a metric, then I can construct an embedding with roughly log n dimensions, so log n lines, okay, so that the distance is always bounded up above by log of 1 over delta times the distance in the metric, and bounded below, that's not right, okay, mark that down, that's an important typo, okay, and it'll also be bounded, oh no, that was correct, okay, it'll usually be bounded below, sometimes it won't be bounded below with probability delta, so it's probably 1 minus delta, it'll be greater than equal to duv. Okay, that's sort of confusing. That's probably the version we'll prove directly just because delta is parameter. But if we set delta to be, 1 over poly n, so I can take the union bound over all pairs u and v, which is really what we need. Okay, we'll get the corollary. So now we have log square n lines, because 1 over delta is poly n. And we're going to be able to embed the vertices onto log square n lines. So that was high probability. If I look at the L1 distance, it's at least the original distance and bounded above by log n. Okay, so we lose a log n factor an approximation. Okay? So it's called log n distortion. Okay? This is a very strong theorem. Log n isn't much. And you're taking any metric and embedding into L1, which is like the simplest metric for us humans who just add things up. It's like easier than L2 metric in some ways, right? Even before when we did the L2 metric was the Johnson-Lindenstrauss stuff, the input had to come from a higher dimensional Euclidean space, right? It required some structure from the input. I had to have the vectors explicitly and stuff like that. Here I'm requiring nothing. Just give me the distances. And then you give me something abstract and I give you something explicit, an explicit embedding. Right? Okay, so it's very strong. All right. So what's the algorithm to do this? Okay. So we're just going to focus on this. The corollary just now said, oh, you need log square n dimensions. But what we're going to focus on is just do log n dimensions first, and then we'll amplify that up to log square n. So what I'm presenting first is the log n version, which will work sometimes for some pairs, and then we'll figure out how to make it work for all pairs with high probability. Okay, so the algorithm is actually very simple. So the idea is we make, okay, so let's start with S1. Okay, so it says that I'm going to first sample all the vertices with probability 1/2. Okay, so here's some set S1, which has lots of vertices in it, or lots of points. Okay, and then the first coordinate is going to be, okay, what is the distance from this set? Okay, so that means every point that's already in S1 is going to get coordinate value 0, because the distance from the point to S1 is 0 if it's already in S1. But for another point, like this one, you'll find the closest point in S1, and that's the distance from S1. Okay, so when I say, right, so you have the minimum over all points in our sampled set, the distance from that other point. Okay, so that will be the first coordinate. The second coordinate is going to sample half as many points as that. So it'll be smaller. Okay, and then we'll compute all the distances from this randomly sampled set. That will give us a second set of coordinates. Okay, we'll do this log n times. So the first set will have n over 2 vertices, then over 4, n over 8, n over 16. Down at the bottom, you're only sampling like one vertex and just computing distances from this point. Right? It's another one of these remarkably silly algorithms. Right? It's very simple. I'm just sampling sets and computing distances from the sets. It seems to be, for some technical reason, advantageous to space them out in powers of 2. Yeah. Yeah, you can just compare all pairs. Which at some level, if all you have is a metric, there's not much you can do. You have to look everything up. You know, if it was like shortest path in a graph, maybe you could do something more clever. Huh? Uh, no, I mean, because we don't have them on a line. So we just have the n by n distances. So I think there's not enough structure. Sorry? Well, once you do all of them, then you have a line. But initially, when getting to order them, you have to compare everything anyway. Okay, so for ease of notation, instead of writing f sub I of u, I'm just going to write u sub I, where it's fixed f. Okay, f is random. Okay, this is got 10 minutes. See what we can do. All right. So, okay, I want to show that the distances I get are less than equal to something, greater than equal to something. So here's the less than equal side. For each particular coordinate I, the embedded distance, ui minus vi, is at most the original distance. Why? Okay, so something like that, right? Let's say that I've ordered U and V, so I can drop the absolute value sign, like one's bigger than the other. And this is less than equal to, do that backwards. Did I do this backwards? All I said that was that we just used the triangle inequality. Okay. Well, I haven't used it yet. So I know that dsu is less than equal to dsv plus duv. And I plug that in. Did I cheat? You're nodding as if you agree with me, but you're also nodding as maybe a yes to I cheated. All right, I'll figure it out later. This is a fun one. Okay, let's do the opposite side. So the opposite side, we don't get the deterministic one. All I'm going to try to show, so before that was just one coordinate at a time, showing that it was dominated from above. Here I'm looking at the sum now, when I say u minus v1 norm. And we're going to show that the expected value is at least some constant times the distance. Okay, so at some level we showed that each coordinate I is sort of shrinking. So there is some risk of shrinking too much. So this says maybe there's some constant, maybe 1 over 10 or something, that we're preserving up to this factor of 10. Okay, and here's where the proof is going to get a little bit delicate. I won't even have you guys guess. Okay. All right, so let me set up some notation. So since we'll be using this a lot, I'm going to let delta denote duv. Okay. All right. And now here's sort of the weird setup. All right, so for each I, I'm going to, okay, so what's the idea? So I have u and v, okay? And what I'm going to do is I'm going to try to find a minimum distance r, okay? So that both of these sets have at least 2 to the I points. Okay, it's possible that one set has many more points. Okay, so r sub I is going to be the minimum point r, such that if I wrote like bur to be the set of points within distance r of u, I want this to be at least 2 to the I, and bvr is at least 2 to the I. Okay, it's sort of weird, okay, but somehow I'm very carefully selecting these radii so that both balls have at least 2 to the I, which means basically one of them should have basically exactly 2 to the I and the other one will probably have more. Okay. All right. So here is the claim. The claim is that for each index I, ui plus 1 minus vi plus 1 is at least, well, the minimum of ri and delta over 2 minus the minimum of ri minus 1 and delta over 2. Okay, so delta just represents an edge case because delta is how far apart they are. And we know that the ui minus 1 plus vi plus 1 is going to be smaller than delta anyway. So that's only, don't worry too much about the delta. So the really interesting case is when the ri's are smaller, in which case it's saying it's bigger than ri minus 1 with constant probability c. Okay? Why is this useful? Is because then if we sum up over all I, the difference in coordinates, I guess I didn't have to write I plus 1, so maybe this is starting from I equals 0 or something. Okay? Then what we'll get is sort of like at the top, we'll get something that's like a delta over 2 minus some r sub h or something where h is whatever, sort of the last one before the delta over 2's kick in. Plus, we'll get this sum of ri minus 1. So this would all be an expectation, and there would be a constant c around this, because with probability c, you get at least this much, so the expectation must be at least c times this much. Okay, and what we get then is we get this nice kind of like telescoping series. Okay, so then we get at least c times delta over 2. That's where it'll add up at the end. Okay, so somehow the claim is that the ith coordinate. Okay, so all right, so let's focus on the most interesting case. So this is where okay, so the case where ri is less than delta over 2. So in this case, we're saying that ui plus 1 minus vi plus 1 is at least ri minus 1 with some probability c, some constant probability c. Okay. All right, so okay, so what's going on? All right, so I'm going to assume, all right, so ri was defined by, we want to make it as small as possible so that u contains at least 2 to the I points and v contains, or the ball around v contains at least 2 to the I points. Let's say it's defined by the ball contains, okay. All right, so, okay, so what we're going to say is, in other words, let's let u, capital U, be the set of points with distance less than, strictly less than x, distance strictly less than ri from u, okay? And I'm going to let v be the set of points x less than equal to ri minus 1, okay? And I'm assuming, otherwise I can swap u and v, so I'm assuming that ri was chosen based on u. Okay, so that means if I had made the radius equal to ri exactly, then I would have at least 2 to the I points. So this set capital U, which is only the points of radius strictly less than ri, has something less than 2 to the I points. Okay. So U has at most 2 to the I points. Oh, we're out of time. So we're almost done. And V has at least 2 to the I minus 1, because that's what R sub I minus 1 means. Okay. All right, so let's look at this. You have this point U contained in this set U. You have this point V contained in this point V. It should be a smaller radius, right? And I'm assuming that the radius Ri was less than delta over 2, right? Delta over 2 would be the midpoint between them. So these balls are disjoint. Okay. All right. So, okay. So I'm looking at S sub I plus 1, right? Now, if S sub I, let's say it's in purple. If S sub I plus 1 samples some points from this set, but no points from here, okay, then Vi plus 1 would be equal to 0, okay, and Ui plus 1 is at least Ri. Oh, no, I'm sorry. So if you sample from inside that ball, then Vi plus 1 will be at most Ri minus 1, and Ui plus 1 will be at least Ri, because you're outside of capital U, but you're inside V, okay? And as a result, you would get Ui plus 1 minus Vi plus 1 is equal to Ri minus Ri minus 1, okay? All right, so what are the odds that happens? Okay, so the odds of the probability that S of I plus 1 and U is empty, okay? So we sampled each point was like probability 1 over 2 to the I plus 1 or something like that. So you get 1 minus 1 over 2 to the I plus 1 to the, there's at most 2 to the I points in there, okay? This is at least a constant. You get like e to the minus 2 or something, okay? Meanwhile, the probability that S of I plus 1 and V is not equal to the empty set, okay? You're sampling, this still has at least 2 to the I minus 1 points in it, right? So the expectation is that you're going to get like 1/4 of a point, okay? And with some probability, I don't know, 1 in 20, you'll get at least 1. Okay, I'll skip the calculations, okay? So you have a constant probability of hitting V, and you have a constant probability of avoiding U. And the last important part is that those two sets are disjoint. So you have a constant probability, you multiply those probabilities together, and with constant probability, you'll hit V and you'll avoid U. That'll give you the gap you need for this coordinate, and then you'll get what you need with constant probability. Okay, so I skipped the case where Ri is bigger than delta over 2, but it's the same idea, just a little bit, there's some nuances. It's not a big deal, check out the notes. And I guess that's the theme. To get the high probability at the end, you would just take the average of log n of these things, and you end up applying a Chernoff bound over the whole thing. Okay, I think maybe the thing to keep in mind is that the algorithm itself was extremely simple. You're just sampling, measuring distances, and out comes an L1 metric that's like as good as you can possibly expect. You get a log n approximation for sparsest cut, you solve all graph algorithm problems, and you live happily ever after. Okay, that's it. Thank you.